Hello and welcome to this chemistry lecture series. In this video, we're going to take a look at chapter 14, section 6, which is going to focus on the other kind of isomers, stereoisomers. Now, we saw in the past video that isomers are compounds that have the same chemical formula. And in the last video, we saw that a structural isomer are compounds that have the same chemical formula but have different structural formula, so they vary in that way. Stereoisomers are the other kind of isomer. They're still going to have the same chemical formula, but in the case of a stereoisomer, they're only going to be different in their arrangement of the atoms in three-dimensional space, meaning they cannot be superimposed. So what does this mean? Stereoisomers are going to have the same atoms bonded to each other. And what that means is that they have the same structural formula. Same So unlike structural isomers, where the structural formula is different even though the chemical formula is the same, with stereoisomers, even the structural formula is going to be the same. The only way to tell stereoisomers apart is to draw them three-dimensionally for one of them, or for them to have a specific type of bond for the other. What this means is that they have different arrangement of atoms in three-dimensional space, meaning they cannot be superimposed. Even though everything is connected to the same thing, they do not superimpose. They're not the same molecule. Now, there are two types of stereoisomers we're going to look at. Geometrical isomers, otherwise known as Cis-Trans isomers, and optical isomers, which are, in all due respect, the hardest one to visualize. Stereoisomers, especially optical isomers, are the ones that give most students issues when it comes to the AICE exam. So again, these are isomers that have the exact same structural formula, the exact same chemical formula, but are still different compounds because when viewed three-dimensionally, they're not superimposable. They cannot overlap with each other, even though everything is connected to the same thing. So let's start with the first type of stereoisomer, geometrical isomers, or otherwise known as Cis-Trans isomers. So geometrical isomers are going to stem from the fact that a double bond cannot have free rotation, unlike a single bond. Now, what does that mean? If we have something a single bond, then I will make it easier. Something like C, single bond C, and then we have, and I'm going to draw this in three dimensions, hydrogen. Actually, I should put that, maybe make that dashed. So we have hydrogen, and let's say here poking out we have a chlorine, and here we have hydrogen, and a chlorine. With a single bond here, this single bond has free rotation, meaning that because it's only a sigma bond holding it together, this bond can rotate around, which means that it doesn't matter whether we grab that chlorine and we put it down here, or if we drew that chlorine where that other hydrogen was, here. Oh, let me change the color. Here. Or even if we put that chlorine in this top bond, which is on the plane of the paper, that doesn't matter. That location of that chlorine doesn't matter because this bond right here, this single bond, can rotate, meaning that these three positions are equivalent to each other. As that bond rotates, so do these three bonds, and so all of these are interchangeable. Whether that chlorine is in this position, or this position, it does not matter. However, with double bonds, that does not happen. If we were to exchange this single bond that we have here for a double bond, so I'm going to erase this because we're going to have three bonds with a double bond. So if we were to exchange that single bond for a double bond between the carbons, And so we would only have 2 here, 2 bonds with our chlorines. Then this changes everything. Why? Double bonds don't have free rotation. Double bonds cannot rotate because of the pi bond that is created between the 2 carbons. If we rotate that double bond, that pi bond breaks. So what that means is that these 2 positions are not interchangeable. If the chlorines are both on the bottom side, they're going to stay on the bottom side. If we swap the position of one of these chlorines for the hydrogen, and we put the hydrogen in the bottom and the chlorine at the top, this chlorine and this hydrogen have no way of flipping. They have no rotation of the bond, meaning this is now a different compound. This is what cis-trans geometrical isomers are all about. The geometrical isomers have different physical properties and might have different chemical properties because if they are across from each other or on the same side, they are actually 2 different compounds. A cis-isomer, and this is why it's called cis-trans isomerism, a cis-isomer has the position of functional groups around the double bond on the same side. Meaning that when we draw those 2 chlorines on the same side, on the bottom or top, that will be a cis-isomer. So if we had, for example, a carbon-carbon bond with hydrogens and bromines, these are chlorines, so very similar. If those bromines are on the same side, like they are here, and by side we mean either top or bottom of the double bond, not left or right, then that will be a cis-isomer. Whereas if they were on the opposite sides, one on top, one on bottom, that's what we call a trans-isomer because they're on opposite sides. So depending on what we have, so we are always going to look for those 2 that are the same. Could be 2 hydrogens, 2 bromines, anything like that. And then by looking at where if they're in the same side or opposite sides, we can say whether they're cis or trans isomers. So here, for example, we have 2 A's and 2 B's, and we're not using actual chemicals here, or actual elements, we're just using A and B. If the A's are on the same side, or the B's are on the same side, then this will be a cis isomer. Here, we have B and D, which are different, but we still have 2 A's. So this will still be a cis isomer because the A's are on the same side of the double bond. Something like this, however, we have A, E, B, and D, 4 different attachments. This will not be cis-trans isomerism. These are still isomers, but these are not in your curriculum. So they're still isomers. They're still a type of geometrical isomer, but not a type we're going to see in this curriculum. But here we have cis-isomers. Trans-isomers would involve the groups that are the same being across from each other. Now, these, like I said, don't actually have to be hydrogens. So here we have the trans isomer we were drawing earlier. If we swap out one of these hydrogens for, let's say, an hydroxide group, OH, this will still be a trans isomer. Why? Because we have those chlorines across from each other. They're still the same group, and they're still across from each other, making this still a trans isomer. So how do we differentiate between a cis isomer and a trans isomer in the name? We will simply, because there are different compounds, we do have to name them differently. We will simply name the molecule that we're looking at. In this case, 1, 2, because we have in 2 different carbons. Dibromo, because we have 2 bromines. Ethene, eth, because there are 2 carbons. Ene, because they're double bonded. And then we will simply put cis in front of the name if it's a cis isomer, or trans in front of the name if it's a trans isomer. So we simply just use those words, cis and trans, in front of the name of the compound. Now, cis-trans isomerism do absolutely need to have a double bond. That's one of the 2 types of molecules that will ever have cis-trans isomerism. Anything with a double bond on a carbon-carbon bond. So carbon-carbon double bond. That's one of the 2 times that we're going to see cis-trans isomerism in a molecule. The other time we're going to see cis-trans isomerism in a molecule is with cyclical compounds. When we have cyclical compounds, when we have rings, we can also have cis-trans isomerism. Very similarly to double bonds, rings are stuck. They cannot rotate. The single bonds in a ring cannot rotate because if they did, the whole ring would get bent out of shape. So single bonds, even though these are single bonds, because they're cyclical, because they're in a ring, they cannot rotate. Meaning they have what we call locked from rotation. They're locked from rotation. Anything that's locked from rotation, like double bonds or cyclicals, are going to allow for cis-trans isomers. And the idea is the same. The idea is that if we have this ring, we can have functional groups that are either going to be on opposite sides or the same side of the ring. Now, this is really hard to see with two-dimensional, actually impossible to see with two-dimensional drawing. We do need to do a three-dimensional drawing. So, for example, if we have this cyclopentanol, and again, cyclo because it's a ring, pent because it's 5 carbons, and because they're all single bonded, O because we have an alcohol, and it is a 3-methyl cyclopentanol because in the third carbon, because this is carbon, this is carbon 1, 2, 3. In the third carbon, we have a CH3, a methyl group. So this is 3-methyl cyclopentanol. But 3-methyl cyclopentanol can have cis-trans isomerism. If both of the functional groups, the alcohol and the methyl group, come out towards us, and we can show that with these wedges, then they're both on the same side of the ring, meaning this is a cis isomer. But if the two functional groups are on opposite sides, meaning one is coming out, the methyl's coming out, but the hydroxide is going back behind the ring, which we show by one having a wedge and one having a dashed line, then that is trans-isomerism, because one is on one side of the ring, the top side, the other one is on the bottom side if we're looking at this ring from the side. Or one is in the front side, and then the other one's in the back side, if we want to see it that way. If we look at it from a side view, this is what we will see. We will have, these are the exact same molecules. If we will have on the left side the cis isomer, where we have that cyclopentane ring, so this pentagon, with the methyl group, CH3, coming out the top, and the hydroxide group also coming out the top. The other way to view it, if you want the groups to be exactly the same, is that we have hydrogens, because remember, each carbon needs 4 bonds, which means every single one of these bonds has a hydrogen on it. The hydrogens are both on the bottom side of the ring. That's what makes this a cis isomer. But in the trans isomer, one hydrogen is on the bottom side of the ring and the other one's on the top side, which makes it a trans isomer because they're on opposite sides. Like I said, the structural formulas will be identical, the chemical formulas will be identical. The only way we can even tell these are different structures is in 3 dimensions, in a 3-dimensional drawing. The easiest way to show this is going to be with our wedges and dashes. So if we have something like this, where we have 2 carboxylic acids in a cyclobutane, if we show both of those carboxylic acids with wedges, we know that's a cis isomer because they're going to be on the same side. It doesn't really matter if we can visualize it or not. We can easily show it with that. And then the trans isomers will have one with a wedge and one with a dashed line. And just for practice, those will be, because it's 4 carbons, it will be but, and because they're all single bonded, this will be 2 carbons with carboxylic acid, COH. So we're going to have 2 carboxylic acids. So dioic acid, because it's 2 carboxylic acids. We'll use the oic acid ending. Di because there are 2 of them. And then this will be 1,3 butandioic acid. because, actually, 1,3 cyclobutandioic acid. Let me put the cyclo in there. It is a cyclical, so we need a cyclo prefix. Cyclo. And it will be 1,3 cyclo, because it's cyclical, but, because it's 4 carbons, and, because they're single bonded, di, because there are 2 functional groups, oic acid, because they're both carboxylic acid, the functional groups, and then 1,3 because these are in carbons 1 and 3. Now, for the blue one, because one carboxylic acid is going down, the other one's going up, this will be trans 1,3 cyclobutandioic acid. And then for the one with the pink here, this will be cis, because they're both coming out the same side. Oops. 1,3 cyclobutandioic acid, because we'll have both of the carboxylic acids coming out towards the same side. So I'll make it the cis-isomer. So that's geometrical isomerism, or otherwise known as cis-trans isomerism, for both double bonds. Anytime we have a double bond, we're probably going to have cis-trans isomer, and cyclicals are also going to have cis-trans isomers. The other type of stereoisomer, which is arguably the most complicated one, is optical isomerism. And optical isomerism is very complex because it requires a lot of visualization. If a carbon in a molecule has 4 different groups attached to it, we call this a chiral carbon or a chiral center. So we can see that here. This carbon, and we'll just use A, B, C, D for now. This carbon right here, because there's a carbon here, right, would be a chiral center because we have 4 different attachments on it. This carbon, a specific molecule, would be a chiral center because you have a hydrogen, a CH3, a COOH or a carboxylic acid, and an OH attached to it. If I wanted to draw this in a skeletal formula, it will be 1, 2, 3. Actually, I'm gonna flip that just to give myself more room. 1, 2, 3. Carboxylic acid, and then this carbon will have the OH and the hydrogen, which we're not showing because it's got the formula. So actually, let me write that OH as a OH. So this is what this is. This chiral carbon is this carbon right here because we have the CH3, the OH, the COOH, and the H that we're not showing attached to it. So that will be a chiral center. Now, why are chiral centers important? Or a chiral carbon important? Chiral carbons are asymmetric. So it gives them the ability to have 2 different versions of what we call an optical isomer. Enantiomers is what we call a pair of optical isomers, or optically active molecules whose mirror images are non-superimposable. So let's make this a little more concise. What is an optical isomer? Optical isomers are mirror images of each other that are non-superimposable, cannot be superimposed. What does that mean? When we put them on top of each other, the 2 molecules are not the same, even though they look to be the same and they're mirror images. So what do we mean by a mirror image? So let's take this. Let's just cut out all of the chemistry for a second and look at this. If we have a molecule with a carbon in the center, meaning we have a chiral carbon with 4 different attachments, A, B, C, and D. If we grab that molecule, because that carbon has 4 attachments, that carbon is going to be a tetrahedral, and we put a mirror in front of it. That's what they call mirror images. Then what we see on the other side of the mirror is this. The D's reflect, the D group reflects, the C group reflects with each other, the A group reflects, and the B group also reflects in the back. So this is a direct reflection of that compound. So it's a mirror image. Now, that mirror image might seem like it's the same molecule, but because this carbon's a chiral center, it is not. That mirror image is non-superimposable, is what we say. Now, what do we mean by that? Let's say I have that carbon or that mirror image, and I'm going to grab these right here, and I'm going to rotate it so that it's in the same position as what I have here. What I will get from that rotation is I will have the C with still my A at the top, but when I rotate it so that the D is still coming out towards the back, like it is here, then what I would actually get is that the C and the B are going to switch places. My C will be in the back and my B will be in the front. If I rotate it so that the D's all the way around, that C, or I could actually, it might be a little easier if you visualize it as the D coming around the back, so rotating it around the back this way so that it's still coming out towards the front. What I'm going to have is that the D and the B and the C are going to trade places. And we can do this a few different ways, right? We just need to follow one compound. Let's say I wanted to do it so that the B is in the same place. So if I wanted to get the B in the same place, I will rotate this essentially 180 degrees so that the B is in the back. But what I will see is that the D, as it rotates, would end up in the front and the C in the back. So these are not superimposable. These are not the same molecule. If you look at it, yeah, the A and the B are in the same place, but the D and the C are swapped. Even though these are mirror images of each other, they're non-superimposable. They cannot be superimposed. When I rotate them to try to overlap them, they do not match. They do not overlap. And we're going to do an activity for this in class to help you visualize this. Because this can be a very tricky situation. If you're not able to naturally visualize things, this can be extremely difficult to see. Now, if we just change A, B, C, and D with actual molecules like here, where we have this chiral center, it's the same thing. This is the mirror image. So again, if I put a mirror here, this is a mirror image that I get in the mirror. The H matches, the carboxylic acid matches, the OH is in the back. But if I rotate this so that the OH is on the left side, like it is here, the molecule I end up with has the CH3 at the top, has the OH on the left side, but once I rotate this 180 degrees, that hydrogen ends up at the front of the molecule. And that COH, CO2H, ends up in the back. So these are non-superimposable. These two are not the same molecule because they cannot superimpose on each other. These are what we call optical isomers, or we say these are enantiomers of each other. That's what this word is. Enantiomers. They're a pair of optically active molecules, which we'll talk about what that means in a little bit, who are mirror images of each other, but they're non-superimposable. They cannot overlap with each other. Now, this can be very hard to see. In order for a molecule to have an enantiomer or to have optical isomers, it needs to have a chiral center. But the problem is that most of the time, the molecules we see are not drawn like this. So let's look at a few examples of that. So let's say we have the following molecule. So let's say we have the following molecule. So if we have this molecule, we might be asked to find the chiral centers in it. So there's a few things that we are going to look for, a few hints that I can give you to finding chiral centers. Because a molecule will only have optical isomers if you have a chiral center. So number one, what are we looking for finding chiral centers? We want a carbon with 3 or 4 visible bonds. I don't know why I didn't write that on the top, but we want a carbon with 3 or 4 visible bonds. So let me rewrite that at the top there. Now we know carbons always have 4 bonds, but we want 4 visible bonds in the skeletal formula, which means this carbon right here could not be a chiral center because this carbon only has 1 visible bond. This carbon right here could not be a chiral center because we have 2 visible bonds only. This carbon right here could not be a chiral center because we have only 1 visible bond. That means there's only 2 carbons. Actually, and let me erase the CH3 because I don't really need it there. There's only 2 carbons that could possibly be chiral. This one and this one, because both of them have 3 visible bonds. So that's the first thing we're checking for. The second thing that we need in order for a carbon to have to be a chiral center is 4 different attachments. Now, what do we mean by that? We need to make sure that none of those 4 things are going to be the same. Now, obviously, like I said before, there's always a hydrogen here, right? There's always a hydrogen attached to that carbon because we only have 3 bonds here. So that's one type. We have hydrogen. Here we have this long carbon chain. So that's a second type. So that's not the same as a hydrogen. But for this carbon right here, this is a CH3. This is a CH3. Because these two are the same, we have 2 groups attached to the carbon that are exactly the same. They're both CH3s. That carbon is not chiral. Remember, a chiral center has 4 different attachments. So because those 2 are CH3s, this is not a chiral carbon. So we can disqualify this carbon as being chiral. So that leaves this carbon right here. Now again, this carbon qualifies because we have 3 visible bonds. We have an OH is one of the attachments, a hydrogen, which we're not seeing, and then we have carbon chains. And now the question becomes, are these carbon chains the same? And I'm not mean just the next carbon over, the whole chain. This chain, if we write as a structural formula, is a CH2CH3. That's what this whole attachment is. Whereas this attachment here is a CH2CH3 2. We have 2 CH3s attached to it. So these are not the same attachment. This carbon has 4 different attachments. We have an OH, an H, a CH2CH3, and a CH2CH3 2. So that carbon here is chiral. This is a chiral carbon, meaning that this molecule does have optical isomers. And then we have the very tough job of drawing that optical isomers. How do we do that? I'm going to show you the easiest way to draw optical isomers when you're asked to do so. The first step is what we just did. The first step in drawing optical isomers is going to be to find your chiral carbon. And then you're going to draw that chiral carbon. So we're going to put a carbon here. That's chiral. So that's already our carbon. That's our chiral carbon there, our central carbon. And then we are going to draw a tetrahedral around that carbon. So we're going to draw in the top a bond, another bond out the back, both of these on the plane of the paper, and then we're going to draw a 3-dimensional tetrahedral, meaning 2 of these bonds are on the plane of the paper, they're just regular lines. Then we're going to have 1 bond coming back. So you can draw this as either horizontal lines like I'm doing here, or we can do it with just a dashed line. Either one works. So, or a dashed line. And then we're going to draw a wedge coming out towards the front. So there's our tetrahedral. And then in this tetrahedral, we're going to put those 4 groups that we just talked about. It doesn't matter which group you put where. We just want to identify the 4 groups and just put them in the 4 corners. So we said we have CH2, CH3, CH2, CH3, an H, and an OH. My general suggestion, put the more complicated group at the top, just so it doesn't move. So we're going to have here CH2, CH3, 2. So we're going to put it as a structural formula here. And then we have the CH2, CH3 group, which we're going to draw here as C. And I'm going to draw it towards the left, H2, CH3, to show that this is a carbon that's attached to this carbon. And then the other 2 groups are OH and H. So we're going to put here OH and H. Like I said, it doesn't matter where you put the 4 groups. You just want a tetrahedral that has your 4 groups around that chiral carbon. And then we are going to draw a mirror. In the middle, we're going to draw a dashed line to draw our mirror. And then we're going to draw the exact mirror image. What do I mean by that? Again, we're going to draw our carbon, our chiral carbon. And then in the mirror image, which I'm going to make in blue, or not in blue, I'm going to make in orange, just to show the difference. We're going to draw our tetrahedral again. But this time, we're going to draw the mirror image of the tetrahedral. Meaning that if we're always going to have this line at the top, the line that came out towards the left here is going to come out towards the right, because it's a mirror image. This wedge is still going to be there, but it's going to come out towards the left side instead of the right side. And now this dashed line, again, is going to be there, but coming out towards the left. And once we draw that, we're just going to copy everything over like a mirror. Meaning the CH2, CH3, 2, that's at the top, we're going to put it here at the top. CH2, CH3, 2. This CH2, CH3 that was coming out towards the back, we're going to draw it on the exact same bond, but in this side, it's coming out towards the right side. So we're going to draw CH2, CH3. You see how that's a mirror image? It's coming out the opposite way. That OH that was in the back, we're going to draw in the back because it's mirrored. And then that H that's coming to the front, we're going to draw towards the front, so it's mirrored. Now these 2 molecules that we just drew are now enantiomers of each other. They're enantiomers, meaning they're non-superimposable mirror images or optical isomers. So these are now optical isomers of each other. This is the easiest way to draw a molecule that's given to you as a skeletal formula as optical isomers. First of all, find your chiral center in the molecule. That's going to be, you're looking for a carbon with either 3 or 4 visible bonds, like this one. And then you're making sure that there are 4 different attachments on it. So this one has 3 visible bonds, which means one of the attachments is hydrogen. We have OH, CH2, CH3, 2, because this is, again, and if you have troubles visualizing that, here's our CH2, and then this is a CH3, this is a CH3, that's why it's CH2, CH3, 2. And then this is our CH2, CH3. And so we have 4 different attachments. This one could not be a chiral center because we have 2 CH3s on it. Once we find that, we're going to make that our central atom in a tetrahedral. And then those 4 attachments, we're going to put them in any order. It doesn't really matter where we put them. What we need to then make sure we're doing is that we are then going to grab that tetrahedral. We're going to draw a mirror, and we're going to mirror it on the other side. Meaning we're going to draw the exact same tetrahedral, but that line that came out towards the left, we're now going to draw it on the right. The wedge and dash that were on the right, we now draw on the left, so it's a mirror image. And then we draw everything where it was. Top line is still the CH2, CH3, 2. The line, the other solid line is the CH2, CH3. And then the dash line is still the OH, the wedge is still the H. And then that's how we draw optical isomers. Every time this will work for you. All right. It's probably the hardest thing you have to do with optical isomers on the exam. Identify the chiral centers, draw the mirror images. So that's what optical isomers are structurally. They're really hard to visualize. Again, their structural formula is the same. Their molecular formula is the same. They might even, if you're not trained and if you do not visualize properly, these two things might look like they're the exact same thing to you. But in 3 dimensions, they're not. Why? They're mirror images that are not superimposable. They cannot be superimposed on each other. Once we turn them, they do not make the same thing. The typical example of that is your hands. If you grab your hands, now put your left hand in front of you. If you were to put your left hand in a mirror, what you will see will be your right hand on the other side. Your hands are mirror images, but they're not superimposable. If I turn my hands, put them in front of you, and turn them so they're palm down, so your palms are facing your desk, and then you try to overlap them with each other, you'll notice that your thumbs don't match up. And that's what non-superimposable means. Even though your hands are mirror images of each other, your thumbs are on opposite sides when you try to overlap them with each other. That's what a non-superimposable mirror image is, and that is what is happening with these optical isomers. Now, what issues do optical isomers have? Optical isomers, for the most part, behave very similarly. The main property that's going to be different for optical isomers is going to be their way in which they rotate polarized light or interact with polarized light. So even though optical isomers are behave very similarly, when we grab polarized light, which is when we grab light and we put it through a slit, so we have a strand up one line of light. If we put that light through a solution of only one polar optical isomer, the light will be rotated in one direction. So when we put light that's been polarized, meaning it's only one line of light, and we put it through a solution of what we call an optically active compound, that polarized light is rotated a specific degree, a specific way, and by a specific amount. If we do that for a solution of 2 opposing optical isomers, 2 enantiomers, what's going to happen is that the light gets rotated by the same amount, but in opposite directions. So if I put my polarized light through one enantiomer, it might be rotated by, let's say, 30 degrees to the left. But if I put it through the opposing enantiomer, it is going to be rotated by 30 degrees, but to the right. So they rotate light in opposite directions. A solution of one enantiomer will rotate light by the exact opposite amount, clockwise or counterclockwise, than the other enantiomer. That's one of the main differences between different optical isomers. The other difference is how they interact with biological enzymes. So some enantiomers or some chemicals like prescription drugs might have one effect with one enantiomer but not the other. For example, ibuprofen has 2 enantiomers. One of them is an anti-inflammatory. The other one does absolutely nothing in your body. So and that's because they interact with the enzymes in your body in different ways. So optical isomers are going to rotate, and this is the one you're going to be asked about in your exam. They're going to rotate polarized light by the same amount, but in opposite directions. So it's important to say that it's by the same amount. So if this one rotated, so if this was the original line, let's say this one rotated by 15 degrees clockwise, then this one is going to rotate the polarized light by also 15 degrees, but counterclockwise. So if this one goes to the right or to the left, this one goes to the right by the same amount. That's how optical isomers interact with polarized light, and also why they're called optical isomers, because they mess with the optics of polarized light. So the other thing we need to talk about is how this all affects cyclicals, because just like we saw with cis-trans isomerism, optical isomerism has some weird interactions with cyclicals. Cyclical compounds have enantiomers if the molecules are asymmetrical. And that's because for a carbon ring to be chiral, the two paths leading to that carbon need to be different. Now, we said that in order for a compound to have an optical isomer, it needs a chiral carbon, or a chiral center. Chiral centers need to have 4 different attachments, but that's kind of hard to do when your attachments are connected to each other. So this carbon, for example, in this molecule, could be a candidate for a chiral center right here. Why? Because we have 3 visible bonds. But you might be thinking to yourself, well, that's not really one attachment or 2 attachments. That's only one attachment that connects to each other. True, but it could still be a chiral isomer even so. Why? This might be one ring, but the 2 paths count as 2 different attachments. If those 2 paths are identical, then there is no chiral center. If those 2 paths are different, then there is. Now, we obviously have here 3 bonds, so we know one of these bonds is, and actually let me do this a different color. We know one of these bonds is going to be a hydrogen. So we have at least 2 different attachments here, the hydrogen and the CH3. What remains to be seen is if these 2 paths are actually different. So from the chiral center, if we count out, we are going to look for a difference in the path. So the next carbon out from the chiral center, carbon 2 from the chiral center is a CH2. Carbon 3 from the chiral center is a CH2. Carbon 4 from the chiral center is a CH2. So because the second, third, and fourth carbon where they meet are identical, that means both of these paths are identical. Meaning that this is not a chiral center in this compound. Because even though you have an H and a CH3, the 2 paths that form the other 2 attachments are identical to each other. We're going to have a CH2, 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 CH2 for the bottom path, and a CH2, 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 CH2 for the top path. And that's because this molecule is symmetrical. It has what we call a line of symmetry. I could actually grab a line and put it through this molecule, through that chiral center, should I say, and this molecule is exactly symmetrical on both sides. This carbon is not a chiral center because it has a line of symmetry. And that's what I mean, that both of the paths around the line of symmetry are identical. Now, if we had a carbon or a molecule where we have, again, a carbon that is a candidate here for to be chiral, we can clearly see that this compound is not symmetrical. If, again, we write a line through that carbon and through the ring, we can see that one side of that ring has an OH and the other one doesn't, meaning that this is not a symmetrical molecule. This is asymmetrical. The asymmetry of this molecule tells us automatically that this is going to be a chiral carbon, because that carbon has 3 bonds that are visible, meaning we have a hydrogen, and it's an asymmetrical molecule through that carbon. However, we can still look at whether the paths are the same. If we look at this, we have a CH3 and an H here, and then the first carbon out from that carbon has a CH2 on one side, but a CHOH on the other, meaning that this carbon is chiral because the paths are not symmetrical. So that's how we look at chirality and chiral centers in a cyclical compound, in a ring. The easiest way to do it is find the carbon that is a candidate for chirality and look for symmetry around that carbon. Now, I should have said that this is also a chiral carbon here. this molecule actually has two different chiral carbons because this carbon is also chiral. We have that 3 bonds being shown, and if we draw a line through it, this carbon is also asymmetrical. And so this is also a chiral carbon. So this particular molecule actually has 2 chiral carbons, which can actually cancel out and give you not optical isomers, but we're not going to go into it. That is beyond the scope of your curriculum. All right. So that's it. That's stereoisomers in a nutshell. I know it's not that simple. It's very complex, very complicated. But that's in essence stereoisomerism, and in its 2 parts. It's optical isomers and the geometrical isomers. That's it for this section. I will see you all in the next